Hey guys, this is Mrs. Lasota. We're going to go through our first SEP 5 intervention focused on trigonometry. So, first and always for our SEP 5 interventions, you'll see at the top we have our SEP 5 skill and the success criteria upon which you will be graded. So that's super helpful to know. How is your teacher going to be assessing you? And we'll apply these as we go through different activities for all of our interventions. So let's start with the very first question, which is a basic SOHCAHTOA question. And even though I'm going to be going through SOHCAHTOA right now, I just want to remind you that on your equation sheet, so on your physics equation sheet, the second column on the right and the bottom goes through all of the different trigonometric functions for you. So you can always, if you're like, I don't really remember, you can look on your equation sheet and it basically has all of the same exact information for you right there. So let's go through this together. Using SOHCAHTOA, we know that sine is the opposite over the hypotenuse. So we'll see this here. The opposite meaning relative to theta, our angle. So sine is the opposite over our hypotenuse. Cosine is AH, adjacent, so the leg of the triangle adjacent to theta over the hypotenuse. And of course the hypotenuse is our longest leg. So our right triangle has our shorter legs, and then opposite our right angle is where we see the hypotenuse. So then continuing there, we have tangent, which is OA, opposite over adjacent. So that's just the basics of trigonometry of SOHCAHTOA. But again, you don't necessarily have to memorize SOHCAHTOA. You have all this information on your equation sheet. So using this information, we're going to apply our trigonometric functions to a problem in context. So I'm going to scroll down. Ooh. What's happening? Okay, so Christy throws a ball across a field to her dog Peyton at a speed of 10 meters per second at an angle of 26 degrees. What's the velocity of the ball in the x direction and the y direction? So the very first thing is just to make sure we understand what's going on in this problem. So we have Christy, and she's going to be throwing the ball to her dog Peyton, and it's going to go woo and to the dog. I have a cat, so all my pictures look like cats. Moving on, we want to make sure that we can draw the triangle we would use for this problem. Well, it told us the initial velocity of the ball is 10 meters per second. So sometimes these silly drawings can be really helpful to help us understand what is the context of this particular question. So my initial velocity is 10 meters per second, and that's at an angle of 26 degrees above the horizontal. We want to know the velocity of the ball in the x direction and in the y direction. So we see our vertical component, that's our initial velocity in the y direction, and our horizontal component is the initial velocity in the x direction. So to solve for VOX, we see that this is our adjacent leg. If that's our adjacent leg, the best trigonometric function to use would be the cosine. So we would say the cosine of theta is equal to adjacent over hypotenuse. So that's our adjacent leg, VOX, over our hypotenuse, VO. If I were to rearrange just to solve for VOX, I can multiply VO to the other side and get an equation of VO cosine theta. So let's apply that and solve. VO is 10, and then cosine of theta, which is 26 degrees. So I'm going to go grab my calculator and we'll solve that together. So the cosine of 26, so I just pop in cosine of 26 and multiply that by 10. Be sure that you're in degree mode on your calculator, and you should get 8.9, or about 9 meters per second. Make sure that you always include your units because that is part of our success criteria. So this part, we just figured out, hey, we need to use the cosine, we applied that to the problem, and then we solved. We're going to do the same thing for VOY. This is opposite my angle, so now I know I need to use the sine of theta. Sine of theta is VOY over VO. And I'll do the same rearranging again. And I'm going to have VO sine theta is equal to VOY. Plug in my numbers again. So it's 10 times the sine of 26. And we get 4.4. So let's say that we were going to actually use these numbers to solve for different things in terms of our kinematics unit. Now we have the initial velocity in the x direction, the initial velocity in the y direction. Remembering that the x and y are simultaneous but independent, we now have the initial velocity in both directions, and we can solve for various things like time, or height, or distance in the x direction. Okay. All right, so now we're going to practice this at a little bit harder question. And ultimately, my friends, what we're leading up to is how do we use this for forces on ramps. So that's where we're going to end today. So moving on to the next page, we'll start with number 3. Okay, so now we're going to be solving for the angle when we don't know the angle. So the angle is our unknown. So the situation is, one day at pickleball, Mr. Feetaway brings a special device that can read the speed of any object at any time. Ms. Cahill hits the ball at an angle over the net to Ms. Frost. Mr. Feetaway determines that the speed as the ball hits the ground is 9.6 meters per second, and the speed at the maximum height is 2.6 meters per second. Determine the Vy and the angle at which the ball hits the ground. So this one's sneaky because it says determine the Vy, which means we must know something else. So what I'm going to do is I'm just going to draw the trajectory of the pickleball, and I'm going to draw in the vectors for the velocities that I know. It says at the maximum height, the velocity is 2.6 meters per second. I know that the vector at the maximum height must only be in the x direction because the velocity in the y direction at maximum height is 0. So the velocity in the x direction must be 2.6 meters per second at our maximum height. We also know the velocity as the ball hits the ground is 9.6 meters per second. That 9.6 meters per second is our final velocity. And this is neither in the x or y direction, it's in both. So we will need to draw in our components. For y and x. But we should know the acceleration in the x direction for something moving like this, a projectile. Acceleration in the x direction is 0. So that means that the Vx here and here should be the same. So I already know the Vx, and I need to draw the triangle to figure out my angle. So I have Vy, which is unknown to me at this moment, 9.6. And Vx, and Vx is equal to 2.6. So first, we're going to solve for Vy. This is easy because we're just going to use the Pythagorean theorem. So we know that a squared plus b squared equals c squared. And in this case, our a squared and b squared are vy and dx. So if we're solving for vy, our a squared plus 2.6 squared is equal to 9.6 squared. I'm going to continue my math over here. So if I go ahead and plug those numbers in real quick, 9.6 squared is 92.16. 2.6 squared is 6.7. We'll go 6.76. And then we have our vy squared. 92 minus 6.67 is 85.4. And that's still equal to my vy squared. So I can just take the square root of both sides to find vy. And I get 9.24. So that's my vy. Now the last thing I need to do is solve for the angle. So the angle at which the ball hits the ground. Now we could solve for either angle really, it doesn't matter. We know that this is our 90-degree angle. I'm going to go ahead and solve for the angle here. But even if we solve for the angle here, they're just the complement of one another. So the angle, let's call it alpha. We know that theta plus alpha should equal 90 degrees. So you can solve for either one. I'm going to go ahead and solve for theta. Now we're going to need to use inverse trig functions, and we could literally use any one of them because we have all the values on all sides of our triangle. What I like to do personally is use the values that I already knew, not the ones I solved for. So I'm going to go ahead and use this value and this value. So my 2.6 and my 9.6. 2.6 is opposite theta and 9.6 is the hypotenuse. So since this is opposite and this is hypotenuse, I'm going to be using sine. So I'm just going to write out the basic equation again. The sine of theta is equal to opposite, so that's my VOX, over my hypotenuse, VO. And since I'm solving for theta this time, I'm going to use the trig function inverse sine. So theta is equal to the inverse sine of VOX over VOY. VOX is 2.6. VOY is 9.6. Sorry, not VOY, just VO. So VOX over VO, we have 2.6 over 9.6. So I take 2.6 divided by 9.6, just 2.71, and the inverse sine function, 0.271. We get 15.7, and the unit on that is degrees, because we're solving for theta. If you wanted to practice inverse trig functions a few more times, you could try using cosine and tangent. You could try solving for alpha. And if we did try to solve for alpha, it should just be 90 minus 15.7. Okay. Last one is in the context of our forces unit. So we're going to be looking at an inclined plane. Now, your best friend in solving any of these problems will always be to draw a diagram, and then of course in the unit that we're currently in is to draw an FBD. So I bet you could start that right now. We have a 12 kilogram box at rest on a 24-degree ramp. So this first is a diagram of the situation. So here's my 12 kilogram box at rest on a 24-degree ramp. If we draw an FBD, we should draw in the surface. We know the force of gravity is always straight down. We know that there must be a normal force perpendicular to the surface. And in this case, since it's not moving, we know we must have a friction force. that means that we'll also have to, using a tilted axis, draw in the components for FG. So we have FGX and FGY. And the question becomes, where do we put the angle? And I think this is difficult for a number of reasons, but I can show you how you can figure it out if you're confused. So we know that this is our angle theta here. And we know that our FG is going to be pointing straight down. If I draw in the FG on my diagram, what happens is I create another little triangle. I'm also going to draw in the components like I have on my FBD, where my right angle is here. So what you should see is two right angles, one that's created by FG and one created by our components. Since we know that this is theta, I'm going to use alpha as an example again, where we know theta plus alpha is equal to 90 degrees. Since the sum of all the angles in a triangle is 180 degrees, that tells us that this angle right here should be alpha. Okay? Just so that everything adds up to 180 degrees. Well, this angle right here is also 90 degrees. So if this is alpha and this is 90 degrees, 90 minus alpha is equal to theta. So that tells me that my angle is here, in between FG and FGY. So if I apply that right over to my free body diagram, this is theta. I think that's one of the hardest parts about starting questions like these on inclined planes, is figuring out where that angle goes. Once we know how to do this process, and we practice it a few times, it becomes really easy to identify where the angle belongs. So I just used the force of gravity and the components, and then all of our geometry knowledge to figure out where that angle belongs. Okay, now it wants me to solve for FG. Friends, this should be easy for you at this point because we know FG is equal to mass times gravity. So FG should be equal to 12 kilograms times 9.8 newtons per kilogram gravitational field strength. FG is equal to 117.6. From there, we just need to solve for the force of friction, static, and the force normal. One thing I want to point out right away is that the normal force and the force of gravity are not equal. In this case, FGX is equal to the static force of friction, and FGY is equal to the normal force. Because this isn't moving, so our net force in both directions is 0. So to solve for the force of static friction, we have FGX minus the force of friction is equal to 0. The net force is 0. FGX is going to be FG, and again, our trig comes back. So here's theta. FG is opposite, so that's going to be sine. And we already solved for FG, 117.6. times the sine of 24. When we apply that, we get 47.8. We'll repeat the same exact process now using the F-net equation in the y direction. We have normal force minus the force of gravity y equal to 0. Again, equal to 0 because at rest the net force is 0. We have normal force is equal to force of gravity, and then again, this is now adjacent, so we get cosine of theta. So applying our numbers one more time, 117.6, cosine of 24, plug that into your calculator. get 107.4. All right, my friends, I will be posting a key for you as well, but hopefully this helped you to understand a little bit more how we use trigonometry in physics class. Tomorrow we'll be focused on derivations and proportional reasoning, so come back to the YouTube channel whenever you need help with SEP 5. Bye-bye.